your confidence would be well-founded if you said, yeah, I'm pretty confident in my ability to separate a mixture. So you're familiar with the fact, you understand the fact that mixtures have to be separated, physical separations rely on differences. Differences in solubility, or differences in magnetic attraction, or differences in visual appearance, difference in heat of vaporization. We kind of did that with the ammonium chloride. So now I want to talk a little bit about the application of that kind of separation in the real world. And the big one is lab chemicals and purity. So what we buy for use here are what are called reagent grade chemicals. And you'll sometimes hear me refer to things as, reagents. Which reagent are you using? Also sometimes called reactant grade, but usually reagent grade. We rank things based on purity. And the purest classification of substance is a reagent grade chemical. You're buying this from a chemical supply company of some sort, and there should barely be any molecules of anything else in it. And you'll usually see on the label 99.99% pure, meaning they have taken great pains to separate out any pieces of contaminant. You might think that food grade would be the most pure. It's not. Your body can handle lots of little impurities and contaminants. I mean, my goodness, the federal government has standards for how many pounds of bugs you can eat per year in flour. You knew that, right? You get little bug bits ground up. It's not a big deal. It's just extra protein. But if you're working in a chemical lab making pharmaceuticals, most of you have probably taken a pharmaceutical at some point. I take a maintenance inhaler every single day of my life because I have asthma. And I'm inhaling a chemical which is traveling into my lungs and which is reacting with my body's chemicals to produce an effect in my body. If you have impurities in the chemicals that are used to make the medications, those can lead to little side reactions, which can lead to unintended chemicals being present in the medication, which can lead to serious side effects. That's one of the things that, so I had my thyroid removed last year. Didn't have a choice. Out it comes. Which means I'm also taking a synthetic form of a thyroid hormone every single day for the rest of my life. And the first thing the doctor said to me was, you do not take generic hormones. Okay, I've been taking generic drugs my entire adult life. Yeah, sure, I'll take the generic, that's fine. The concern is that they may not be as pure. They're often not made in the U.S. They're manufactured in labs overseas. And the concern is that the level of purity in the reagents is not as high, and that there may be not quite as much of the hormone as you think is in it. So reagent grade chemicals have to be the most pure. Food grade is actually less pure. The least pure forms of chemicals we see are what are called industrial grade chemicals. So this chunk of salt, I've shown you this chunk of salt before. It's lovely, isn't it? The top is pretty clear, but as it settles, as you get down to the bottom of the crystal, it's really dark, and that's all kinds of contaminants. There's all kinds of other stuff in here. Could we purify this? Yeah, absolutely. You could do a physical separation. You could grind this into powder, and you could separate out the non-soluble bits in here. It's probably bug parts and ancient fish poop and who knows what else. This came from a salt deposit underneath Lake Erie, from a salt mine about 2 miles down. No, a mile down, something like that, down there. We could purify this, but it's a lot of bother. And the salt from that mine ends up getting scattered on roads all over the state of Ohio, all over the Midwest, actually. Do you think they do a whole lot of purification on salt that's going to go on the roads? No. Ancient fish poop, dead bug parts, doesn't matter. There's enough sodium chloride in there that it effectively changes the melting point of the ice. It keeps the roads slushy, not frozen. We're good. That's about the level you're looking at with industrial grade chemicals, where impurities don't matter as much. So you don't take as much care or as much energy, as much time to do the physical separation that would be necessary to purify this. You guys all know how to do a purification. So now I'm going to airdrop you something. The particular periodic table that I shared with you, and the one that I'm using up here, and the one that you'll get before the year is over, probably 6 or 7 or 8 or 10 copies of on paper. Every year we have a sort of informal competition to see who has squirreled away the most copies of the Van Brainer periodic table. I think the record is 10. I lost my periodic table. Can I have another one? Sure. I lost my periodic table. Can I have another one? Sure. Before you know it, you got 10 stuck in a notebook. I like this one. This was developed by a chem prof at a little tiny college called Widener University. And it's very simple. It's very clean. It's got just the information you need on it. You'll note that the names of the elements are not written on it, just their atomic symbols. And you've probably been used to using ones that have both names and atomic symbols. I think it's ridiculous to ask you to memorize. I know somebody who used to teach physical science used to have people memorize the first 20 elements and their symbols. You're going to look it up. I'm not going to do that, but by probably Thanksgiving, I'm just going to assume that I can use the symbol and you'll know what it is. You're going to be using this one and you'll get used to it. You'll just learn it without thinking about it ever again. But this is the periodic table. And like I said, it is the chief source of information about elements. We use it on a regular basis. And two things to be very aware of first off. We talk about groups and periods. And groups are the columns. Years ago, this was when I taught physical science, I had a sophomore, I guess, this is when we taught it to sophomores, propose a mnemonic for that, which is gravity pulls things down. Groups go down. It's a pretty good mnemonic. I like mnemonics. It's the only way I remember anything. So groups go down. Periods, and there's no handy mnemonic for this, go across. And we usually actually talk about them in terms of going this way. Same way we read a book. But the periods are the rows. And within groups, we tend to see patterns of chemical reactivity and other chemical characteristics. Within the periods, there are some patterns, but they're not regular. So the place that we see regular, predictable patterns is really within the groups. So I said the periodic table is the primary source of information about the elements, and what I forgot to say is, what are elements? And you know this from physical science, but it just bears sort of touching on. They're substances where the characteristics of the substance are the same when we get down to a single atom of the substance. So if it's on the periodic table, it's an element, and if it's not on the periodic table, it's not an element. The order that they are arranged in on the modern periodic table is in increasing number of protons. So every time you step across from here to here, from here to here, you're adding 1 proton. And that'll become important as we talk more about configuration on the periodic table. Gesundheit. There are 4 major classes of elements, and we're just going to talk very briefly about them. These are things that you should be somewhat familiar with from physical science. The first type of element we're going to talk about are the metals. And this is actually most of the periodic table. The metals are the most common elements in the universe. And metals are not just what you think of as metals. Sodium's a metal. Calcium's a metal. Lithium's a metal. So basically, the metals, and I'm going to lose my line here, comprise the entire left side of the periodic table. Yes, I have to make an L with my hand. I think of it as the west coast of the periodic table. So the metals comprise most of the periodic table. They're good conductors, both of heat and electricity. With one exception, they are solids at room temperature. They tend to be shiny. They tend to be malleable, which means able to be hammered into sheets, and ductile, which is able to be pulled into wires. They make our lives possible. Copper especially. We are living, again, I'm reading right now about stuff in Bronze Age Britain. Britain in the time of the Saxon invasions. And, it's the Bronze Age to the Iron Age, there's a way in which this is the Copper Age because all the electricity that we are so accustomed to that makes our lives possible is flowing through copper. Of course, it's not the Copper Age. That was a different thing. People were actually using copper axes. Try chopping a tree down with that. But copper's important. Lithium, you're probably all not carrying it around, but over there you probably have a battery that's dependent on lithium ions. Metals make our lives possible. And lithium is also used medically. There are a couple metals that have medical applications. There are also metals that are important in the body in their ionic forms. Sodium and potassium are critical in cellular functions. You have sodium and potassium pumps in every cell in your body. And without them, you wouldn't be having this conversation or you wouldn't be listening because your heart is a muscle that's dependent on those ions being in the proper balance. So that's the metals. So there aren't a whole lot of nonmetals, and if anybody here has a sibling or anybody else who is everything they are not, who's their polar opposite, that's the metals and nonmetals. If the metals are, the nonmetals aren't. So metals are good conductors, nonmetals are lousy conductors. Metals are solids at room temperature, nonmetals tend to be gaseous at room temperature. And the nonmetals are this group over here. So it's a small group, many of them diatomic in nature. Oops, I left out phosphorus, but we're not drawing hard and fast lines. There, that's better. So they tend to be brittle, where you can take a metal and you can hammer it into a thin sheet. If you do have a solid compound made of nonmetals, they tend to shatter rather than be able to be manipulated in their solid form. A lot of these are gaseous at room temperature, and a lot of them comprise our atmosphere. Carbon, oxygen, nitrogen, compounds thereof like CO2, H2O, are major atmospheric components. Then we have the metalloids, also sometimes called semi-metallics. You'll see them listed either way. They're kind of neither fish nor fowl. They have some characteristics of metals. They have some characteristics that are more common in nonmetals. And some of them behave differently depending on the conditions of temperature and pressure that they're under. So the semiconductors that make possible our phones, our iPads, our computers, silicone chips, that's a semiconductor. And it is a metalloid. It behaves differently. It is a semiconductor because it only conducts under certain conditions, which is useful if you want something that can kind of blink off, on, to store data. This is a tiny little group. Usually it looks, we do something like this. So it's this kind of tiny little wiggly line, and I can never remember if germanium is classed as a metalloid or not. So I'm fudging. I have to look those up. The big ones I know off the top of my head, but the rest of them I have to look up. And I'm not so worried that you have them committed to memory. Okay, the last type of element, these are noble gases. It is group 18, this last column on the periodic table. As you would imagine from their name, they are gases at room temperature. Peculiar. They're non-reactive. They generally do not form compounds with anything else, and that all comes down to their electron configuration, which we'll talk about later in the year. They are perfectly content where they are. They don't need anything, and therefore they just don't react. They don't tend to form compounds. Neon, argon, krypton, xenon, when you talk about neon lights, each of these has their own distinctive color, so we tend to talk about them all as being neon lights. In reality, they're different noble gases used in those tubes. And you basically put the gas in a tube under low pressure and you run electrical current through it, it glows, which gives us our familiar lighting. Argon is also used. Has anybody here ever welded? Anybody done gas shielded welding? We're done gas shield? Okay, so here's the theory behind it. You take a piece of metal and you heat it up enough that it's fairly molten so that you can join two pieces of metal together. Fantastic. Well, hot metals tend to be more reactive. And so that hot metal bead, it's called a bead, that joint, will actually react with water vapor in the air, and as it cools, it can start to look rusty already. You've got this brand new shiny metal joint and it's rusting already. That's really disappointing. So you can do what's called gas shielded welding, because the hot metal is reacting with the oxygen specifically, both in the water vapor and in the air itself, because of course rust is just iron oxide. What if you are able to push the oxygen out of the way until the metal cools so it's not so reactive? Well, you'd need to push it out of the way with a gas that's non-reactive. And so gas-shielded welding typically employs argon to push the oxygen out of the way so that that nice, new, fresh, hot metal bead doesn't have oxygen to react with and therefore doesn't rust. Why is it important that we're conscious of the types of elements? Well, it's really handy, actually, if we're aware of these categories of elements, and I'm just putting these same slides back in, because what it allows us to do is classify quickly new substances that we encounter. So if we find a substance and we see that it is shiny and conductive, we would tend to guess that it's probably a metal. If we find a substance and it's gaseous and brittle in its solid state, we would tend to assume that it was a nonmetal. Whoops, already did that one. If we find a gas that is non-reactive, we would tend to think that perhaps we had discovered a new noble gas. So knowing the characteristics of these groups as they're arranged periodically helps us to classify new materials. And that's one of the things that analytical chemists do, is classify new materials. Has anybody, well, it's kind of old news now, the rovers that have been scouring the surface of Mars, was it Opportunity rover, and was the other one Spirit, I think? And they've got an entire little analytical chemistry lab in their belly. So basically they scoot along the surface, they grab samples, they pull them up into the chem lab, which is probably, you know, a quarter of the size of this tabletop, and they analyze them. And they can analyze, they can do preliminary analysis, which shows, you know, what percentage of the Martian surface is composed of metals. Are there solid forms of nonmetals? On this planet, do you know what element is the most common element in our crust? And when I say crust, I mean the actual rocky part of the Earth, not the oceans. That would be such a common guess, and yet it's oxygen. Huh? Most rocks on this planet are made up at least partly of silicon dioxide. That's one silicon bound to two oxygen. So oxygen actually comprises a large part of our crust. Well, it would be really interesting to know if the Martian crust is similarly composed. So we can classify materials according to the type of element they are, and it's useful because we've got these broad categories. Okay, questions? Comments? Concerns? Questions about homework? Questions about anything else? Okay, so here's the plan. Tomorrow we will grade homework, and tomorrow, of course, you guys have a double period, so my timing is all off. We'll grade homework. I'll pass back the labs. We'll go over all the labs tomorrow. So we'll spend one half. And the way I do this is we typically do a trade and grade. So you'll trade papers with somebody at your table. You'll grade theirs. They'll grade yours. You'll write somewhere on the top, graded by. I have this funny thing about language and precision of language. Most of you are college bound. Most of you are heading off to do bigger, better, more wonderful things. You should be able to express what you know in writing. And so I am a bit of a stickler for things like sentences that make no sense, such as, it's like the other one, huh? That would just be marked wrong. So we kind of go around. I have you read from the paper that's in front of you. We say yes or no. I'll record the grades. Sometimes I spot check, sometimes I don't. Sometimes after you've graded the homework, I'll have you turn it in, and I'll spot check to see if if you and your buddy are in collusion and you're not marking stuff wrong. Sometimes I don't get to it. So we'll do that. Then I'll pass the labs back. We'll discuss the labs. Material from your labs, the kind of calculations you did on your labs, is fair game for the test. And the whole test should fit into just Wednesday. Oh, we have a 2-hour delay Wednesday, huh? Well, that stinks. Well, we'll see. We'll just see how it all unfolds. Some part of your test will be Wednesday. It might be the whole thing, and it might not. I'm not sure yet. So we'll see how that goes. And then Thursday we'll start Chapter 2. So hopefully I'll have your test back to you Thursday. If it was the whole thing, if not, we'll finish up on Thursday. And we'll start Chapter 2, which is where we start the math. So, other questions, comments, or concerns? Okay, you got time to work.